Good afternoon, everyone. I'm Huixia Ren from Professor Chao Tang and Liang Yichen's lab in Peking University. Today, I will share you our story about the phase-locked pancreatic alpha and beta cells. In experiment, we do calcium imaging to study the islet cell activities. We do this because the calcium influx directly triggered the vesicle fusion and hormone secretion. We further designed a microfluidic chip to provide a controllable and stable imaging environment. Under the constant high glucose stimulation, islets show typically calcium oscillations, and the different islets show different oscillation modes, such as the fast oscillation with period around 20 seconds, slow oscillation with period around 3 minutes, mixed oscillation with the fast oscillation on top of the slow oscillation. During the last 40 years, it was almost dominated. These come from the beta cell heterogeneity, so they simplify the islet to the beta cells. However, when we dissociate the islet into single beta cell, we found only slow oscillations in the high glucose stimulation, with a period around 5 minutes. It suggests that the minimal unit of different oscillation modes is probably the islet. So, our ultimate goal is to study the relationship between the oscillation modes and alpha-beta cell paracrine interaction. It requires, first in experiment, we need to achieve reliable cell type identification. We do this by generating transgenic mice. Spatial tempo analysis could provide critical information about the cell-cell interaction. And finally, we want to understand and test our hypothesis by building mathematical model. Given the islets show huge heterogeneity, we first want to test if the mode is a stable property or not. So we use a repetitive high glucose stimulation protocol, and we found the oscillation mode is highly reproducible among the islets within the fast, slow, or mixed oscillations. So it proves the calcium oscillation mode is a very robust intrinsic islet property. Then we wonder whether and how the alpha and beta cells in an islet are coupled. So we generate a transgenic mice where the alpha cells specifically labeled with the green calcium sensor G-camp, and the beta cells are sparsely labeled with the red calcium sensor R-camp. And we found under the glucose stimulation, alpha and beta cells are globally phase-locked and show iterative oscillation activity. And later we realized this phase-locked alpha and beta pattern is generally true among the slow, fast, and mixed islet. So the phase-locking pattern is independent of the oscillation period. Then what's the similarity and the difference of the phase-locked dynamics in different oscillation modes? To answer this, we further quantify the phase-locked alpha-beta cycle. Here, the period is defined as the waiting time, a duration between the two beta cell peaks, and the activation of alpha cells in between separated the whole period into two waiting time. The red shadow area represents the waiting time of alpha cell after the firing of beta cell, and the green shadow area represents the waiting time of beta cell after alpha cell. The phase shift is given by the ratio of T beta alpha and T. We found the phase shift depends on the period in an inverse proportional function manner, and this is because the waiting time of alpha cells is about a constant value. It's roughly 20 seconds. However, the waiting time of beta cells linearly correlated with the period, which tells us the waiting time of beta cell actually determined the period T. So here, if the beta cell wait a short time, then the eyelid show fast oscillation. If the beta cell wait a longer time, then the eyelid shows slow oscillation. We further assume maybe this pattern is generated by different paracrine secretion, maybe the glucagon value amount secreted by the alpha cells. As a student from mathematics background, we test this hypothesis by using mathematical models. Here we simplify the eyelid into two coupled secretory oscillators, which is described by the variable theta, which is mainly driven by two forces, the intrinsic force and the paracrine force. The intrinsic force describes the oscillation frequency of the isolated single cells. For beta cells, it's about 3 minutes, and for alpha cells, it's about 40 seconds. And when the cells pass the phase pi, they will secrete hormones to instantaneously speed up or slow down their neighbor, according to the stimulatory or inhibitory paracrine interaction. And the coupling strength is described by the parameter K alpha beta and K beta alpha. By tuning the coupling strength between alpha and beta cells, we found the model also displayed three types of behaviors: the slow oscillation, fast oscillation, and mixed oscillation. And moreover, the alpha and beta cells are stably phase-locked in all these patterns. And similar to the experiment, we can also further analyze the relationship between the waiting time and the period and the phase shift. Again, we found it highly consistent with the experimental finding, where the phase shift depends on the period in an inverse proportional function manner, and that's because the alpha cell wait a constant time, and the beta cell's waiting time determine the period. Compared to the experiment, model can tell us what determined the waiting time of beta cells and the oscillation mode. As we can see here, the most critical parameter switching the oscillation modes is the K alpha beta, which corresponds to the glucagon concentration. We test our prediction by pharmacological perturbation by adding glucagon, and we found the glucagon speed up the slow oscillations into the fast oscillation by specifically decreasing the beta cells waiting time, while keeping the alpha cells waiting time still constant. So here we understand the waiting time of beta cells actually depend on the glucagon concentration. And if the alpha cell effectively secrete a large amount of glucagon, then the beta cell will be quickly kicked up. Then the paracrine force would dominate and eyelids show fast oscillation. However, when the alpha cell failed to secrete enough glucagon, then the beta cell will behave just like the isolated single cell. Then the intrinsic force would dominate it, and the eyelids show slow oscillation. In summary, we found that the alpha and the beta cells are globally phase-locked in eyelid, and the waiting time of alpha cell is constant, and the beta cell's waiting time determined the period, which is regulated by the glucagon. The mathematical model reviews the oscillation modes is determined by the coupling strength of alpha and beta cell. Finally, I want to thank the people behind this work for creating such an interdisciplinary mentoring and collaborating environment, and thank you for your listening.